So, as Alex said, I run the Neuroscience Microscopy Service. It's in the basement of this building. So, if I can be of assistance with the equipment that I have down there, please don't hesitate to get in touch. So, I'd like to continue some of continue Alex's questions. So, let's have a show of hands. How many people here have a good understanding of numerical aperture? I'm going to be talking about laser scanning confocal microscopy, 2-photon microscopy, and structured illumination microscopy. And I'm going to start out with a discussion of numerical aperture. So when you're thinking about microscopy, most people, the first thing they're thinking about is magnification of the objective. But the little number that follows the magnification, the NA, is also very, very important. So NA, numerical aperture, measures the light collection capability of the objective, and it's intimately related with the resolving power of the objective. Okay, so the equation is given here. So if you look at the angles over which the objective can collect light, that half angle, mu, here, is measuring the angle from the optical axis to the edge of the light collection. So the sine of that half angle, and then times the index of refraction of the immersion media, defines the numerical aperture. Okay, so if your objective could collect over a full 180 degrees, that half angle would be 90 degrees. The sine of 90 is 1, and the index of refraction of air is 1. So if you were collecting a full 180 degrees with air, you'd have an NA of 1. So typically, the highest NA for an air objective that you're going to see is going to be 0.9, 0.95. So you get the idea of how much of a solid angle that objective can collect. And then with water, the index of refraction goes up, and with immersion oil it goes up even higher. So immersion oil gets you up to 1.5, and so you're able to collect even more light from the sample. And why this is important is that, the size of the feature, the resolution of the objective is going to be determined by the numerical aperture. So the larger the numerical aperture, the more light you're collecting, and the smaller the features that you can see. Okay, so as the numerical aperture increases, the size of the point spread function. So if you have a very tiny spot point source of light, it's going to get diffracted by the optics. So that the light from the point source gets smeared out into a disk. Looks like this with intense peak at the center, waves going off. But the airy disk size is the distance between the peak and the first minimum. And that's going to define the resolving power of the objective. And you can see that as the numerical aperture increases, the size of that diffraction, the disk is going to get smaller and smaller.
So I have a question about that, Andrew. Would that mean that if you had two objectives, one which was, let's say, a higher magnification, which you might a priori think is, oh, I want to use a higher magnification, if it has a lower NA, would you actually potentially be better off using the next magnification down, knowing that you're going to collect more light? Like you would actually be able to resolve a signal.
So you could resolve a 40x 1.4 NA or 1.3 NA objective is going to have higher resolving power than a 40x 0.95.
Right.
Or a 60x that's 0.9.
So depending on what you're trying to look at, it might actually be better to use a lower power that is collecting more light. It don't depend on what you're looking at, but
so the resolving power is going to be determined by the numerical aperture.
Okay.
Yes.
In the first image, do you think that's actual reality? Because in hard imaging, that's kind of band of light is only narrow to the center of the lens, the first image, right? It should go to all collected by the whole length, right? Instead of just center of the lens.
So it's showing, it's basically showing it backwards. So if you're projecting a column of light, it's going to get through, from the back aperture, it's going to get focused down to a point like that. But the diagram is a little.
Yeah, I thought, in my mind, I think it's more related to the distance of the lens to your specimen. Here it's the same distance.
Yeah, right. As you go up in numerical aperture, the working distance is going to be shorter and shorter. You're going to be closer to the objective. Yeah. So this is not to scale. Right. Yeah.
Okay, so that's sort of another trade-off.
That's another point. Yeah, you're going to be working closer and closer to your sample. There's going to be it's going to also have less depth of field, a smaller depth of field with a higher NA.
Okay.
That's also not a fundamental limit, though. Like, there are long working distance, high NA objectives,
Right.
especially. I mean, there's a lot of new ones, actually, like
Right.
a 20x 1.0 with like a 20 millimeter working distance.
Right.
You just pay for it, right?
Yeah, and it's about $30,000. Right? Yeah.
And this diagram is a little bit deceptive in that obviously it's actually the same objective illustrated
Right, yeah.
across. And what's
Right.
changing here is how
It's the
much
cone of light
is
that they
the
put
cone of
through.
light that's going into the back of the objective, not the
Yeah.
other way around.
Yeah. The principle of a laser scanning confocal is illustrated here. So the idea is that you're going to illuminate the sample with laser light. There will be a scanner, so scan mirrors that are going to sweep the light point source across the back aperture of the objective. So there will be one mirror that's going to scan in the X direction and a second mirror that'll move the beam in the Y. Then there will be a tube lens that will expand that beam so it will fill up the back aperture of the objective, and then the light reaches the objective, is focused down onto your sample, and then you can see there's there would be light, a cone of light coming down, illuminating the sample above and below, and it's going to collect light above and below the focal plane. So the solid line is your desired plane of focus, and then there's also going to be light collection from below that plane and above that plane. So the emitted light is collected by the objective, and there's a dichroic mirror so that the excitation light passes through that mirror, and the emitted light is going to get reflected towards the detector. And then in the detection beam path, there's a pinhole that's at a conjugate focal plane with the objective. So the beams, the light beams, are coming to a focal point right at the plane of the pinhole, just as they did in front of the objective. So the light that comes from the plane of focus below your desired level gets focused here, and the plane above focus would fall into focus at this point. So you can set the size of the pinhole to block the rays of light from above and below the focal plane. Okay, so this is how confocality is achieved. So you're going to be only allowing light from some region above and below the focal plane to reach your detector, and the rest of the light is discarded. Okay. So this is, that's a schematic, and now here's the guts of a Zeiss scan head, so you can see all the parts. And I'm just going to walk through this light path from start to finish, and we'll talk about the various controls that you'd have in the confocal software to adjust, so you can control what it is you're seeing. Okay. So at the back of the scan head, the laser light is brought in on fiber optics, and those are combined. And then there's a primary beam splitter that's going to reflect the desired laser excitation lines down to the mirrors. And on the way back through, the emitted fluorescent light will pass through that mirror. So those are dichroics that are going to reflect the excitation light and allow the other bands of light to pass through.
So at that gold port down at the bottom left, that's where the light's going out to the specimen and also coming back through.
Right.
Okay.
So the light hits the scan mirrors down here. So we've got X mirror and the Y mirror. Then there's a scan lens. It's expanding the beam, so it'll fill up the back aperture of the objective. And then it's attached to the side port of the microscope and gets reflected up to the objective, illuminates the sample, and then the emitted light comes back through that same path. Gets focused down onto the mirrors, bounces off of them, and then passes through. And the rest of the optics then are designed to separate the light out spectrally and send it to one of the 3 detectors. Okay, so there's various schemes in different scopes. This particular model is using dichroic beam splitters and bandpass filters to select the light that's getting to these 2 detectors. And up here, there's an array of photomultiplier tubes with a grating out in front of them. So this is spreading the light out into a spectrum, and then you can choose which region of the spectrum you're going to actually read from the detectors, or you can read out from the individual PMTs in the array and get an emission spectrum in about 10 nanometer bands. Okay, so there's a spectral detector and then 2 side-on photomultiplier tube detectors that will just receive all of the light in the band that's coming through that's been selected by the bandpass filter.
And how much does this cost?
This scope and its current version are about $420,000. $400,000. It depends on exact, there's various bells and whistles that you can get. The scope that I recently got an LSM 710 system with 3 detectors. It doesn't have a spectral detector and an environmental control system, and that was about $420,000 after tax. So a more modern version doesn't use emission filters, and they've got fancy optics that use prisms to select out various parts of the spectrum and send it to the the blue side detector or the red side detector here. So
for different wavelength, do you use the same pinhole, or you usually just
in this design, it's the same pinhole is used for all the channels.
or that affect the resolution by different regions?
Yeah, the pinhole size, the optimal setting for the pinhole will vary by wavelength. So you'd set the pinhole to accommodate the lowest, the shortest wavelength that you were detecting at that particular time.
When you say optimize pinhole, what do you mean by that? For experiment, when you reduce the pinhole, you kind of increase the resolution, right? But you also lose the line and also lose the signal noise ratio.
Yeah, I'll be talking about all of these things as I continue on. So we'll cover that. Yeah. So in this design, the pinhole there's a separate pinhole for each light path, so you can set the pinhole optimally for each particular wavelength. It's a small adjustment, but there's a single master pinhole, so all of the detection paths are going through the same pinhole.
So you can adjust it, but you just can't
You can adjust it
fast enough in order.
You
to
couldn't
get-
adjust it. You wouldn't want. Well, you can work this system. You could acquire your channels sequentially,
Yeah.
so you could adjust the pinhole size for each one, if you so desired, right?
Yeah.
But sometimes for speed, you want to collect a red and a green at the same time, or a red and a blue at the same time, and in that case, you'd have to pick a compromise pinhole set. But it's not that big of a deal. What you have to control, there are several controls that will affect the intensity of the light. Okay, so obviously the power of the laser, how much laser power you allow to come through to the sample, how fast you scan the mirrors. So the mirrors you can adjust the speed of the mirror, and depending on how long you dwell at each pixel, if you slow the mirror down, you'll have more time to sample at each pixel, and if you speed it up, less time, so less light. The size of the pinhole, so you can set the pinhole to match the point spread function of the objective, so that you're collecting at the diffraction limit, or you can open it up a little bit more and collect over a thicker Z slice and get more signal that way. So you can sacrifice some Z resolution and a slight amount of XY resolution to increase your sensitivity.
So Z is really the sort of, that's the thing.
That's the main influence of the pinhole.
Gotcha.
Is how opening the pinhole up is going to increase your optical section thickness. And then last, the detector is a photomultiplier tube. It's very fast response time, not, maybe 25 to 30% quantum efficiency depending on the PMT. But basically, a quick way to describe how these work, it's a vacuum tube, light comes through a window and causes electrons to be let loose. And then there's a chain of electron multiplication. So you're applying a voltage down the length of the tube. It's accelerating those electrons. They're hitting another surface that's going to cause more electrons to come loose, and bouncing on down through the detector. There's multiple stages of that electron multiplication. And so at the end, you're collecting a current from all of the this cascade of electrons, and that's going to be proportional to your signal. For each channel, you'll have a control, something like this in the software, where you have a control to change the laser power, you have a control to change the pinhole size, you have a PMT gain control, and then there's going to be a black level control, this digital offset. Okay, so the laser power on a confocal will be regulated by, in most cases, it's an acousto-optical tunable filter, and it's a fancy way for changing the light level very, very quickly. But in the software, the control that you see is very simple. You're controlling the percentage of the laser power that's reaching your samples. If you wanted to double the laser power, you double the percentage. If you want to cut the laser power in half, you cut the percentage in half from where you are. Okay. The pinhole size, there's a handy calculator that will set it to 1 area unit. So it'll be the optimal size for the numerical aperture of the objective that you're working with and the color of light. And then it'll give you a measure here of the optical thickness that setting would collect. Okay. And essentially, if you double you go up to 2 area units, you're going to double the section thickness, and so on. Okay, and then on the PMT gain, typically PMTs respond with a doubling in the output intensity with a 50-volt change in amplitude. And the range here is going to be from typically 0 to 1200, 1250 volts. Okay, so for every 50-volt change, you're going to see a doubling of the signal.
So Andrew, can you briefly, and some of the other guys might be getting.
Yeah, I'm going to talk about where you should set your gain.
Yeah.
But the answer is in the middle. But I'll talk about why it's the middle.
That's right. But my point was going to be that there should be a balance of how much light you put into the system. That's going to be matched to your fluorophore, which I think you're also talking about.
Yeah.
And then how much you crank up the gain of this thing to get a good signal versus get super pixely noisy.
Yeah. So I'm going to leave those discussions for Jesse.
Okay.
He's got a lot to say on that. But yeah, you basically have a light budget. You have a certain number of fluorophores in your sample. Exposing them to intense laser light is going to lead to losses of those at some bleaching rate, and you have to parcel out how it is that you're collecting them. So how you decide to set the gains is going to be, the things that guide you are going to be different if you have a fixed sample versus a live sample that you want to image over time, or something that you want to take Z-stacks with versus just a single plane. So. Yes?
If you're working with a spinning disk that has fixed pinhole size, like what is the best way, or is there any way to change your section thickness? Or it's just fixed?
It's fixed, so I think not.
Changing the objective?
So you would have to change the disk, yeah. Yeah. So with a spinning disk, the pinhole size is going to be matched to a particular objective NA, and so the system is going to be designed to work with that specific objective. And if you move away, so changing your NA would do it, but yeah.
Optimal thickness you got from the one aperture unit is same as the Z resolution of the objective, or is different?
One area unit setting for the pinhole will get you the optimal, it'll allow you to sample at the optimal resolution of the objective. Okay, so the point spread function is always going to be like football shaped. So in XY, it's going to be much narrower, and in Z, spread out about threefold, typically threefold larger than in XY. So the Z resolution is going to be worse than in XY, but this pinhole size will allow you to achieve the best Z resolution that the objective could deliver.
Because what I heard is when you really do the scan, the best resolution or step, the thickness of the section, it should be around half of the Z resolution.
So yeah, so if you were doing a Z stack, you'd want to set your step size to be half of this, because you need to sample that that point spread function at least at the Nyquist rate, so at least twice, in order to be able to digitally capture the optical information.
So we got the value from here, then divided by 2.
That's right.
To set your Z step size, correct?
Okay.
Yeah.
There's no way the pinhole is going to make your point spread function smaller, right? So you can't, you couldn't possibly put a pinhole in and then have the light only be coming from half of the, yeah.
But that's a good sort of practical point, though. So for this example, if it's calculating a 0.9 micron section, you want to sample at 0.45 and do 0.45 micron
0.45
steps.
micron steps, right, to get the optimal resolution.
That's right.
And all these calculators are so this is to deliver the best that the objective can do. So if what you need to see is a larger feature, then it's to your advantage. It can be to your advantage to open up the pinhole, gather more light, make your system more sensitive, and scan faster, sample more coarsely. So you have to, the buttons are handy calculators for optimal highest resolution, but your mileage may vary. If what you need to see isn't right at the diffraction limit, then you can tweak things to optimize the performance for what you need to see. That's first the settings for specific channels, and then for the entire scan, you're going to have a scan speed. So this will determine how long the PMT will be sampled for each pixel. It's also going to determine the size of the pixels, because the scan is going to be over a fixed distance, and then however many pixels you divide that up into, that's going to determine the size of a pixel. So there will be a calculator button to set the pixel size to match the resolution of the system, and that'll again be determined by the numerical aperture and the shortest wavelength of light that you're collecting. Okay. Other settings, there's going to be an option for averaging, so you can do signal averaging to improve the signal to noise. And Jesse, I believe, is going to be talking a lot about noise sources, so I'll leave that to him. And then you're also digitizing the signal from the PMT, and you can do that at 8 bits and have smaller file size and 256 gray levels. You can go up to 16 bits, have more gray levels, bigger files. And then another very important point is how you display the information in the software. So taking the pixel information that you have from your image and displaying it on the screen so that you can see the minimum intensity and the maximum intensity. So the software is going to have controls that are going to allow you to. So here's a graph of the possible pixel intensities, and the shapes here are showing what was actually collected for 4 different channels. So you can see if you tried to display the full dynamic range, your sample is going to look pretty dim here. And if you adjust the contrast and bring the brightest down to the top end of your signal, you're going to be matching the dynamic range of your sample to the dynamic range of the screen and be able to see it better. Okay. Just a quick couple examples of the kinds of things that you can do with the confocal. So here, these are line scans from cardiac myocytes derived from iPSCs. So the scan, a single line can be scanned very, very rapidly. It's microseconds per pixel, so here 100 pixels in the millisecond range. And then you can take a whole bunch of those, line them up, and see the calcium transients. So this is labeled with flow 4, and you can see the calcium transients in a spontaneously beating cardiac myocyte. It's also great for immunofluorescence. So here, looking at subcellular features, looking at the translocation of this protein smoothened to the primary cilium, which is labeled with acetylated tubulin. So when the cells are treated with sonic hedgehog, that activates smoothened, and it translocates to the primary cilium. And it's, another thing that can be done is to tile images, so you can build up a larger field of view from high resolution single panels. And so this is maximum intensity projection from a Z-stack in optic tecton that Alex generated. So you can see.
Kind of blab down.
No,
Our
that's
value.
actually, those are excellent.
Oh.
Sorry, did you say that was a Z-stack going from top to bottom there?
So what this
no.
is he took a Z-stack through the optic tecton and
Like-
tiled. Yeah, so he's getting multiple
the
planes.
Z-stack is taken in, or like through the plane of the board,
Yes.
like this, and then it was 15, I think, images going like,
3 by 5.
3 by 5, yeah, across the entire thing.
And then they're projected down. A maximum intensity projection is collapsing that Z-stack down into a single plane.
And then some of the software that Forrest is going to talk about will do the harder work of stitching it all together, so it makes one nice big image.
Another type of microscope that I have in the facility is a 2-photon microscope. So this uses infrared illumination to excite the fluor. So infrared photons have less energy, and it takes the simultaneous absorption of 2 infrared photons to excite the fluor up to the excited state. And you only get that photon flux right at the focal plane of the objective. So here is shown, what we're looking at is a cross-section of a fluor. It's probably fluorescein in a cuvette. And here they're illuminated with the same objective. And this is single photon illumination, so you're seeing the light coming down to focus, but you're also getting the out of focus cone of light from the objective and above the objective. So the objective's down here, and focusing the light down to the sample, and you see that cone of excitation that's out of focus above and below. And with the 2-photon, only a small volume right at the focal plane of the objective is excited. Okay, so infrared illumination doesn't scatter as much. It'll penetrate deeper into the tissue. It can be useful for imaging into cortex through cranial windows. You can use it in tissue slices to look at dendritic spines. And So that the illumination is fairly similar, but it's a pulsed laser scanned across the sample and focused onto the sample. And then, since you're only illuminating right at the focal plane, any photon that comes off, whether it's scattered or not, can be collected. So we don't need a pinhole. So the light is just collected very close to the objective and then imaged again by a PMT. Okay, so again, like with the laser scanning confocal, the single photon confocal, this is a scanned. There's going to be scan mirrors scanning the 2-photon beam across the sample.
Excuse me?
Yes.
The photon from the specimen, when it enters the objective, before reach the PMT, during this period of time, the photon could be disappeared or absorbed by the objective or not?
Typically, that's not going to happen because the objectives are transparent to light. So, but the photon, you're imaging deeper into the tissue. So on the way out from where it's emitted, it could get scattered by
You talking
by
about
the
the
tissue.
excitation photon or the emission photon?
The emission photon.
The emitted photon.
Yeah, once it enter the objective, before reach the PMT, during that period of time, is there any changes in the photon numbers?
In the photo what?
The photon
Photon
numbers?
Yeah, they can get absorbed. I mean,
Yeah.
objectives vary, but there's typically like 70 to 90% transmission in the visible. So, depending
We're
on
talking about length, right?
what's that?
Objective length, that's what I'm talking about.
Well, I'm just saying, you put a photon in to the objective, there's a 70 to 90% chance it'll make it out, depending on the objective.
I mean,
So,
sometimes I'm worried that the photon got to be going to all directions, not just the
no, the collimation properties are different, but typically those are pretty good. But it's typically absorption events inside the objective that would where you would lose light rather than scattering.
Okay. So with the 2-photon, you're using infrared light, so there's less scattering, deeper penetration. It's a nonlinear absorption process, so you get a restricted excitation volume. And you can also use that for photoactivation. So on the setups in my facility, the systems have 2 sets of scan mirrors and 2 lasers. So one laser can be used for imaging, and the second laser with the second set of mirrors can be used to uncage compounds or photoactivate compounds. You can work at a different wavelength. You could release caged glutamate and at a very focal volume in your sample. So you could release it right at one specific dendritic spine and not at its neighbor and look at the responses.
Yeah.
For live imaging applications, I've heard that light is harmful to cells in general, so too much radiation is bad. Which is a 2-photon with a longer wavelength mean that you can image with less phototoxicity?
Probably the biggest advantage is that you're not illuminating so much above and below the focal plane. So you're limiting right to the focal point of the objective, but you can still crank up the laser and you can cut. With these, it's infrared. You can turn it up and you can boil the tissue very, very quickly if you're not careful. So you can get too much light in there too.
Yeah, I mean, I guess a couple points are that, certainly bluer light is more toxic to tissue. Obviously, you don't want to go into the UV. But that bleaching can cause photo damage just because bleaching typically involves like an oxidation event. And so, as you said, because you're getting all of this out-of-plane fluorescence with just a single 1-photon system, as opposed to this very punctate spot, proportionally, all other things equal, you're going to get more damage, but
With 1 photon.
with 1 photon, because you're
Right.
going to get more bleaching. But then but the longer wavelength should be better as long as you don't accidentally hit the jog button on the motor that controls the mirror and go up to too much power to kill your mouse, which can happen.
It's happening.
You should really put something over that jog button. Yeah.
So that it doesn't increase the resolution. The resolution is similar to what you get with the confocal. Okay, and I'm running long, so I'm thinking I should just leave.
Okay.
I was going to talk about structured illumination microscopy, but I think I'll leave that for another time. So
Okay,
we don't
that
go
sounds good. And we'll put the slides up
further.
online as well.
But I do have some sample images from the 2 photons. So here, this is from Maya Jurisic and George Vidal and Carlos Schatz's lab. So this is, I believe it's hippocampal neurons from a mouse that's YFP mouse. So it's 5% of the pyramidal cells are expressing GFP. And they were just looking at spine dynamics over time. So repeated Z stacks and a maximum intensity projection, and we're seeing dendrites retracting and over time, looking at dendrite dynamics. Okay, and then this was an example of a photoactivation experiment. So in zebrafish, James Chen from the James Chen lab, Shan Ouyang and Ilya Shestopolov. So that they're using caged morpholinos, which were injected to the zebrafish embryo at the 1-cell state. They allowed the animal to grow to 10 hours post-fertilization, and then we illuminated a specific region that was going to give rise to notochord cells. So this was a no-tail morpholino. So before photoactivation, nothing's there. And after photoactivation, so they put in a photoactivatable protein along with the caged morpholino, so you could see where the photoactivation took place. And they were able to cause the notochord cells to become medial floor plate cells instead of differentiating to notochord. Okay, so spatially restricted photoactivation or spatially restricted uncaging.
Okay. Great. Any other questions for Andrew?
Sorry about it. The uncaging is very the laser spot. The size of the laser spot is same as the point spread function, the disk size.
So it's a different process for 2 photon, but it's going to be the 2 photon point
It's
spread
one
function.
photon, 2 photon is
Pardon?
I mean, 1 photon in case is, for example, UV light uncaging, the laser point.
So if you did single photon uncaging, yeah, you're going to end up with uncaging over a much larger volume.
Right.
Right.
Exactly how big the size of the beam is determined by the objective, right? That's same as the resolution of the objective.
Yes.
Yeah.
Yeah.
The spot
And-
you're
yeah.
talking about, the resolution of the objective is exactly determined by the point spread function, which is how the light is focused down to a spot.
Right.
And so that's both the resolution of your imaging technique and the size of the spot that you're
The laser
causing.
point.
Yeah.
It is exactly the same thing.
Thanks.
Yeah.
I think one point though is that between UV and 2 photon, the size of the point spread function of any objective, so like back when he had this equation for NA that involved the NA, it also involved the wavelength, so that with a shorter wavelength light in the same NA, you're going to get a tighter spot than a shorter wavelength light than than a longer wavelength light with the same NA. So, and it's typically linear. So, yeah. But in 2 photon, is it the square? Because it is nonlinear, you have 2 photons coming in at the same time, right? So I think it might be the
it's the
square.
intensity of the beam square, but there's something else that's
Okay.
actually more complicated, right?
Okay. Too advanced for all of us.
Yeah.
All right.
All right.
Roughly
cool.
roughly the wavelength is double, so roughly the size is twice as big, and then it's squared, so it's back down. Right?
Okay.
There's a calculator. There's a deconvolution software called Huygens, and it can calculate and give you model point spread functions for various NAs of objectives, wavelengths of light, and whether it's single photon or 2 photons. So you can go to the Huygens website and play around with that calculator and see the size of the PSF.
Great. Thank you, Andrew.